Hello, and welcome back to Techniques of Political Analysis. We are continuing our discussion of part 2 of visualization tools, that is, tools that don't have any built-in data, but allow you to upload data of your own. And in this video, I want to talk about the problem of visualizing networks. Now, sometimes you have data that take a network structure, maybe countries in the international system, or people in some sort of organization, or a group of friends, a social network, right? And what you want to do is visualize that network. Well, there aren't all that many pieces of software that allow you to do it, and one that does, and does very well, is called Gephi. And you can go to Gephi.org and download a copy of Gephi onto your own computer. It's free. They ask for a donation so that they can continue to develop it. And Gephi, it's got a lot of features that you could use in a professional network visualization capacity. That is, people who study networks for a living use a lot of the measures that Gephi generates about networks. And that's actually to our considerable advantage, because it allows you to do things with network visualizations that you might not have thought of doing. So I'm going to walk through an example here using my own Facebook network. And you can follow along and do exactly the same thing. The first thing to do is to download the Gephi program from Gephi.com. Then what you need to do is go to Facebook and use an application called NetViz. And what that does is it sort of walks through your Facebook social network and pulls down all of your friends and figures out which of them are connected to which other friends. And once you've done that and saved it in a GDF file, that's one of the formats of network files that Gephi is able to read, then you can import the data into Gephi and visualize your Facebook network. So that's what we're going to do right now. Okay, so I'm not going to go through the process of using NetViz to download the data about your Facebook Friends network. It's pretty straightforward. You just launch the NetViz application. It's going to ask you for permission to access all sorts of things about your Facebook network, your friends, their friends, what they like, what they don't like. It'll ask you for access to your bank account, all the usual things. Just give up any illusion of privacy that you might have thought you had and click yes. So once you've done that, it lets you go download your personal friends network as what's called a GDF file, file with a GDF suffix. That is the kind of network data file that Gephi can read in. One thing that happens on my system, probably happen on yours, is that the system will insist on saving this as your data file name .gdf.txt because it thinks it's a text file. Just eliminate the .txt suffix for whatever difference it makes. Then we fire up Gephi, and you get this welcome screen, which asks you what you want to do. Do you want to start up a new project? Do you want to open an existing graph file? And we tell it we want to open a graph file, and we want to open Facebook data.gdf. Now, right out of the box, this is a pretty unexciting looking network, or it will be once the overview clicks in. So what this is telling you is that there are 519 nodes, and the nodes are people. That means I have 519 people in my friends network. The edges are connections among the nodes. So in my friends network, there are 7,146 connections from one friend to another. That's mainly what you need to know. Also, this isn't what's called an undirected network. That is, it's impossible for one person to be a friend of another person without that other person also being the friend of the first person. ties go both ways. Twitter is a good example of a directed network, right? You can follow someone and they don't necessarily follow you. This is undirected. If you are friends with someone, they are automatically friends with you. So we tell it the graph is undirected, and we tell it to import, and now we get the fairly unexciting looking graph of what my social network looks like. But that's okay because it's going to be getting a little more interesting in a few minutes. So the first thing that we need to do is figure out how to make this less clumpy, less undifferentiated. And that's what the layout section over here to the side does. You choose an algorithm for laying out your social network, and that algorithm changes the shape of the cloud. You can experiment with different ones, see what you like. I generally end up going with Force Atlas or Force Atlas 2, which is a really neat algorithm because what it does is it holds clusters of observations together while pushing them apart from one another. So it shows you basically clumps of friends in your friends network, groups of friends that are connected to one another. And when you run it, what you see, right, all of a sudden, boom, is that I've got 3 main clusters of friends. Now, we don't know who these folks are just yet, but there's one big cluster here, another cluster which is somewhat connected to this first cluster, and then a third smaller cluster that's sort of off on the side that is not as well connected to this first group. So how do we figure out who these people are? Well, we've got 3 tabs up here. Overview, which is where we are now. The data laboratory, which shows you the data. If you want to take a look at your friends network, you can do this. You can look at the nodes, which are, again, are the individual friends. Here's Tom Flores, node ID 3230. And we can look at the edges, which are the connections between friends. So Tom is connected to probably 20 or so of my other friends. Okay? Now, but what we're interested in now, in taking a closer look at who's who in this network, is the preview screen. Start off by hitting refresh. The preview screen basically gives you a pretty version of what you saw in the overview window. But it also allows you to modify. So, for example, we can use a small font here because if the font is too big, it's gonna blow everything up. Even with this, it's going to be pretty dense. So we can choose a small font, Arial 8, and then when Gephi comes back, we say Show Labels, okay, and then we hit refresh. And now what we can see is all of these nodes have names attached to them, labels. So we can zoom in a little bit, and what I can tell by looking at this big cluster is that it's made up mostly of people I know in Columbus. Friends that I've made socially, people that I've gotten to know in the food world through my work with Slow Food Columbus, and that's mostly those 2 groups. If we take a look at the second network here, right, this network is a network of academics, and these folks are people who know each other, and I'll expand this out a little bit so it's easier to read. These are all people who know each other from graduate school, from meeting each other at conferences, from reviewing one another's papers, and there's some, as you can see, there's some connections between people in town and people in the sort of academic circles in which I travel, and they tend, for the most part, to be other academics. Professor Verdier, Eleonora Mattiacci, one of the graduate students here, Ted Hoff, who was a professor here until recently. So they're the connections between these 2 clusters, the sort of social foodie cluster in Columbus and the academic cluster down here. What about this third cluster? This, as you might anticipate, consists of family. These are folks who are mostly out in California, which is where I grew up. This little cluster down here is people I got to know in high school. They aren't my family, but they know some people in my family. And then we have a few sort of isolated people. Here's Traylene Turner, who was one of the first people I met when I came to town, but doesn't really know many of the other people in my network. Kathy Fish, the wife of one of my mother's colleagues. David Scabin, who's a chef in Italy that I happened to meet. Meredith Strauss, who was a former student of mine from when I was in graduate school. These are all people who are isolated in this diagram because they're not connected to any of the other people that I'm connected to. So that's my social life dissected for your viewing pleasure. What can we do with this that is analytically interesting? One thing we can do, so for a little background, network theorists really like the idea of centrality. They like to measure which nodes, or in this case people, are central to the diagram. But what's interesting is there are different ways of thinking about what centrality means. So we're going to take a look at one of them now. It's called degree centrality. And degree centrality is probably the most intuitive kind of centrality that you would imagine. It just refers to the question of who has the most connections. In this graph, who has the largest number of friends. That person has the highest, in the words of network theorists, the highest degree centrality. So we can go up here to ranking. These tabs allow us to apply color or weight to different nodes and different edges. Now, as you would imagine, we're looking at edges, and then we can look at nodes. And this reflects the color of the node. This gives you the size and weight of the node. As you would imagine, this allows you the possibility of plotting all sorts of different dimensions of data. Here, the only data that I've really pulled down are the individuals and the number of connections that they have, but we could potentially plot more dimensions than that. So let's color in these observations based on their degree centrality. And right away we can see a couple of individuals in my sort of local Columbus cluster who are pretty high in terms of degree centrality. Now if we go down to Force Atlas and we click Prevent Overlap, and then we hit Run just briefly, what that'll do is spread the observations out a little bit so that the nodes are not sitting all on top of each other, and we have a slightly better chance when we go to the preview window of seeing who's who. So, who in my network of friends has the highest degree of, or the largest amount of degree centrality? If we refresh the view, and we may have to change the size of the text again. We'll bring it down to 8 point. Okay. So let's see how it does when we refresh the view here. All right, and now people are not overlapping nearly as much. And what we can see, we should be able to see when we zoom in. I apologize for the lag. It's taking a little bit longer to do this than I would like. So the first red dot here is Bethia Wolf, who's a friend of mine and who runs Columbus Food Adventures, and she is incredibly active on social media. She's got lots and lots of connections in my Facebook network. The other is Liz Lessner, who owns a number of local restaurants, Betty's and Surly Girl and Dirty Frank's and the Jury Room and so on and so forth. And she is also incredibly active on social media and very proactive, as a matter of fact. If there's anything wrong with one of her restaurants and somebody complains about it online, the odds are very good that they'll get a note back from Liz offering to make it right. So those are the two people in my network who are the most connected as measured by degree centrality. Well, what other kinds of centrality do we have, or can we look at? If we go over here to Network Overview, these are algorithms that allow us to run some calculations about the network to get statistics that we didn't already have. So the first thing I want to do here is to make a couple of calculations about graph distance. And we're going to calculate a couple of other kinds of centrality. Betweenness centrality measures how often, as it says here, a node appears on the shortest paths between nodes in a network. That is, if I want to go from person A to person B, how often is the node in question on the shortest path between A and B? And I'll illustrate that in just a moment. Now, closeness centrality is sort of like, I think of it as 6 degrees of separation centrality. That is, the fewer degrees of separation you are from everyone else in the network, the greater your closeness centrality. So let's calculate those in Gephi, or tell Gephi to calculate those. And now they show up. First of all, we get graphs of the distribution of betweenness centrality and closeness centrality. So for betweenness centrality, what we can see is most people have a betweenness centrality of 1. That is, they're not more or less sort of between one group of people and another. There's one person up here at 55 who is remarkably central in terms of betweenness. Now, closeness is a little bit more varied. We have more people who are, you can think of this as sort of the Kevin Bacon scale, right? More people who are sort of very close to other people in terms of number of connections. And that's going to be, it won't be unrelated to betweenness centrality. Now, we can color in our observations. Now that we've run these calculations about network diameter, we have these statistics available to us where we didn't before. So we can look at betweenness centrality and apply the algorithm. And that's actually a very, very different outcome than what we just had, right? Because all of these nodes that used to be sort of orangish and pinkish, now they're just plain white. And there's a node right here that's extremely red. Now, what does that tell us? What would you expect? Who would you expect this one person to be? Well, if you think about it, there's one person who's missing from this network, and that's me. I am not a node anywhere in my own social network. These nodes are all my friends. I am not my own friend. I'm not listed in the network at all, which creates some sort of interesting dynamics. So this person is the person who most effectively, who's the biggest bridge, I guess you could say, between my friends in town and my family. That is, normally you would expect that to be me, but it's not, right? Because I'm not in the graph. So, if we go to preview and think to yourself, who you think that might be, we refresh the view, which only takes 30 or 40 seconds, and we zoom in, and we can see that person who is a bridge from all of my friends in town to all of my family is my fiance, which is kind of again, the main reason that she ends up being the shortest connection from my friends in town to my friends at home, my friends and family at home, is that she's the only one out of that network who knows lots and lots of my friends and family. So she ends up being essentially serving as a proxy for me, connecting these people to each other. Now, if we look in my family, we can also see that my younger brother shows up as more of a bridge from one group of people to another. We look up here. I think that's probably Bethia Wolf again. And down here we've got Ted Hoff, who probably knew more people before he left OSU. I think he knew more people in town than most of my academic colleagues. Same for Eleonora Mattiacci, one of my graduate students. They both know a fair number of the people I know in town, and they know a lot of the academics that I know. So that's why they show up as bridges here. So these are people who really exist in sort of, bridge one cluster to another. Now, what else can we look at? Well, if we come back here and look, instead of betweenness centrality, at closeness centrality, this is sort of the 6 degrees of separation centrality, we see a considerably more even distribution of closeness centrality than of betweenness centrality. There's one more example that I want to, and I don't want to take up too much time here, but there's one more understanding of centrality that's worth checking out: eigenvector centrality. Now, this is the kind of centrality that Google uses to come up with its rank of the importance of web pages. And the short version is that, here we get the distribution again, the short version is that a node is important if it's connected to other important nodes. Now you'll notice that definition is kind of circular, because in order to understand whether the nodes that it's connected to are important, you need to know whether it's important and vice versa. So this eigenvector centrality is calculated via an algorithm called factor analysis that you can get to know better when you're in graduate school or taking a statistics class. And if we apply it, what we're getting are basically the people who correspond to the top hits on your Google search page, right? The pages that are connected to the other most important pages. In this case, people who are connected to other really central people. You can think of it as sort of like the cool kids in high school or something along those lines, right? They're all connected to one another. Well, who are the cool kids in my diagram? We refresh the view. I think we refreshed the view. There we go. And they're pretty hard to see. So what I'm going to do is go back to the overview. Not as easy to tease out as the other ones were. I'll just grab them here. And you can sort of click and drag. Right? This isn't going to affect the calculation of the network statistics or anything else, but you can pull people out of their central locations in a network and just sort of put them off to the side to see who they are. If you can click carefully enough, you can do this. Here's another one. And let's see, maybe one more here, fairly orange. Trying to find the most eigenvector central connections in the network and pull them. Here's another one. So let's see, and maybe this person right here. No, that looks like a little bit less central. So let's just see who we dragged out. We can go back to the preview window. And we hit refresh to reanalyze our connections. We're going to have to zoom backward a little bit to see who's here. And that's a little bit too far. So one again is Bethia Wolf, who is, if there's any lesson to this lecture, it's that Bethia Wolf is incredibly well connected on social media. Ann Evans, who helps run Columbus Underground, Alexandra Fox, Liz Lesner again, and Wolf Starr, who runs the Small Business Beanstalk. These are all very reasonable people to expect to be highly sort of central to a social network, both my own social network and the town's. So this gives you a sense of what you can do in Gephi. The last thing I should mention is that once you're done formatting your network in the way that you want to format it, and you've got all of the connections the way you want them and everything else, you go down to the export window here, export tab, and this brings up a window that allows you to save this as whatever you want to call it. My friend, PDF or something along those lines. Got a somewhat clunky window to use for saving. And then once you've done that, you can double click on the My Friends file, and it'll open in preview, and you've got it as a PDF, so you can blow it up basically to sort of arbitrarily large sizes. So this is this in a nutshell is how Gephi works, and you should feel free to play around. I didn't really do anything in the overview window with the size of the nodes. I mentioned that it was possible. If you want to do that, you'd go up to this sort of diamond-shaped tab here, and let's say we wanted to go from 3 to 8, for example, and make the nodes bigger if they are more central. Maybe I didn't get my 8. There we go. Okay. And we want to make the nodes bigger. All right, let's try 15. There we go. Now we're getting a somewhat better view of larger versus smaller nodes, and you can see it showing up here. So again, one of the things that I think is important to be able to do in visualizations is to represent as many dimensions of the data as possible. So if you want to do something like represent, if you want to see how much eigenvector centrality corresponds to degree centrality, for example, we can use the size dimension to capture degree centrality and the color dimension to capture eigenvector centrality. And we can see that there's a pretty high correlation between the two. So, in any case, this is just to sum up, this is not only the only way of visualizing network information that we have, but it's actually a very good one. It's got lots of options. It's relatively straightforward to use. It can be a little bit clunky here and there, but it has a lot of things for you to explore, and it can produce really professional, clear visualizations of what a network looks like.